Consider the mapping w equals z squared. We can consider this as a mapping from the z plane to the w plane. Let's look at z equals 2 plus I. Let's get its image. Well, we just square 2 plus I and we get 3 plus 4i. This here is our z plane. So this point with coordinates 2, 1 represents the complex number 2 plus I, and its image in the w plane is 3 plus 4i. We can think of that as the point 3, 4. Now, the point 2 plus I in the z plane lies on the two lines x equals 2 and y equals 1. So here is the line x equals 2. It's a vertical line through 2 on the x-axis. Y equals 1 is a horizontal line through 1 on the y-axis. Let's suppose we get the image of y equals 1 under our mapping. Well, a general point on this line has the form x plus I. So the real part of any point on this line is, the imaginary part is 1. But the real part x can be any number. So we want to get the image of this, we want to square x plus I. So here we go, we square x plus I, we get x squared plus I squared. Well, I squared is minus 1. So the real part of w is x squared minus 1. The imaginary part is 2x. We will call the real part of w u and the imaginary part v, just like before. We are interested in the relationship between u and v for the image of x plus I squared. So we're mapping from the xy plane to the uv plane. So a general complex number in this plane has the form x plus yi, and a general complex number in this plane here has the form u plus vi. So to find the relation between u and v, we have to eliminate x between these two equations. So from this equation we see that x equals a half v. We could plug a half v in here. If we do that, we get u equals a quarter v squared minus 1. We can multiply all this by 4 to get 4u equals 1v squared minus 4. That's one way we can do it. It's done slightly differently here. This equation is multiplied by 4 and then this equation is squared. So 4x squared will appear in both of these. Well, whichever way you want to do it, you'll end up with v squared equals 4 plus 4u. So this is the relationship between u and v for the image of the horizontal line y equals 1. You see, this involves a squared term, so we have some sort of a curve. So here it is. It passes through 3, 4, of course, because the point 2, 1 is on the line y equals 1. Now let's get the image of this vertical line x equals 2. Every complex number on this line has real part 2. The imaginary part can be anything we like. So we call the imaginary part y. It's the notation we use for the imaginary part of our complex number in the z plane. So we want to get the image of that line. So get the image of this general point on the line. We have to square this. Now the real part is got by squaring both of these terms. 2 squared is 4. If we square this, we get y squared I squared. Well, that's y squared by minus 1, or minus y squared. So the real part is 4 minus y squared, so that's our u. And the imaginary part is 2 times 2y, which is 4y. So now we can get the relationship between u and v for the image of the line x equals 2 by eliminating y between these two equations. So we get y equals a quarter v here, plug a quarter v in here, and we get u equals 4 minus y squared over 16. Multiplying all this by 16 would give us this result here. So we get v squared equals 64 minus 16u. So that's a curve passing through the point 3, 4. Now notice the angle between these two lines is 90 degrees. Let's consider the angle between these two curves. Well, to get the angle between two curves, we get the tangents to the two curves at the point of intersection of the two curves. The angle between two intersecting curves is defined to be the angle between the two tangents to the curves at the point of intersection. So we're interested in finding this angle. We will consider the slopes of these two tangents. Now the dependent variable for each of these curves is v, the independent variable is u. We know that dv du is the gradient or the slope of the curve at any point. The slope of the curve is the slope of the tangent to the curve at any point. So we need to get dv du for each of these curves. So let's start with v squared equals 4 plus 4u. Now v is not given explicitly as a function of u, although we could get the square root of the right hand side and get dv du from that, but we can also use implicit differentiation. We just differentiate the left hand side with respect to u. So really this is an application of the chain rule. So v is some function of u, so if you imagine v is an expression in u in brackets, we differentiate around the brackets to get 2v to the power of 1, then multiply by the derivative of what's inside the bracket, which would be dv du, if we think of it like that. As for the right hand side, the derivative of 4 is 0, the derivative of 4u with respect to u is 4. Rearranging, we get dv du equals 2 over v. So that's the slope of the curve at any point. So to work it out at the point 3, 4, we just need the v value. The v value of the point is 4. So we just plug 4 in here, we get 2 over 4, which is a half. So the slope of this tangent is a half. That's not surprising. It has a positive slope, as you can see. Now the other tangent appears to have a negative slope. Let's get that. So we need to get dv du for the other curve. It's the slope of the other curve. So we can use implicit differentiation like before. Differentiate this with respect to u. We get this here, divide across by 2v. We get minus 8 over v. And at the point 3, 4, v is 4, so we plug 4 in. So we get minus 2. Now notice that the slope of one of these tangents is the negative reciprocal of the slope of the other tangent. So if we invert 1/2 and change the sign, we get minus 2. That tells us that these two tangents are perpendicular to each other. Or another way we can say it is that the product of the slopes is minus 1. If we multiply 2 by minus 1/2, we get minus 1. So the angle between the tangents is 90 degrees. So that means that the angle between the two curves is said to be 90 degrees. So this angle is preserved. In general, if any two curves in the z-plane intersect at a point z0 and their image curves under the mapping w equals f of z intersect at w0, which is f of z0, the image of z0, and if the angle between the two original curves at z0 equals the angle between the image curves at w0, then the mapping is conformal at z0. So we can actually have any two curves intersecting at z0 here. To get the angle between the two curves, we just consider the slopes of the tangents to the curves at the point of intersection of the two curves. So here I'm indicating the angle with a dot. Okay, if the mapping is conformal, then the angle between these two tangents here will be the same. It is a fact that an analytic function is conformal everywhere except where f prime of z is 0. Now this is not obvious and I won't prove it in this video. I might prove it in another video. Here we have the function w equals e to the power z. Now it is a fact that this function is analytic. It's analytic everywhere actually. And it's also true that f prime of z is never 0. F prime of z is e to the z, and that's never equal to 0, no matter what z is. So this means that there are no points for which this function is not conformal. So this function is conformal everywhere.